Okay, let us start. In order to save time, you will see me twice because I don't want to change between the Blackboard recording and sharing my screen. So let me just very briefly introduce cellular automata. What we will do in, you can choose where to look, it's good. You can, wait, what am I? Good. What we will do now is basically become cellular automaton engineers, and we will spend a good chunk of time really going through the technical details of the construction of a von Neumann self-replicator in a cellular automaton. So let me just very briefly introduce cellular automata. So we will fix d some positive integer, and we will call z to the power of d a d-dimensional lattice. And we will call each element of this lattice a cell. And each mapping C, okay, so fix S some finite set. We will call each mapping from Z to the power, or from this d-dimensional lattice into S, a configuration or an S configuration. Next piece of terminology. Let N and K an element of Z to the D to the K. This will be called a d-dimensional neighborhood. And for each cell, N induces its relative neighborhood. Which is essentially just so we are now ready to define what a d-dimensional cellular automaton is. So a d-dimensional cellular automaton CA from now on is defined by we have fixed the dimensions. So S, a finite set of states, N, a neighborhood, and finally F, where this K coincides with the side of the neighborhood, a local update rule. So this induces a global map Okay, one more piece of terminology is that by S to the power of Z to the power of D, this is essentially exactly the set of all such mappings. So this is the configuration space. So this induces a global map F, which manipulates the configuration space as follows. For a configuration C and a cell V, we have that the image of C at position V is exactly just the application of the local rule at the location of the. Essentially, we look at the first neighbor of the cell V and at the second neighbor of the cell. Yeah, so essentially for each cell, we look into its relative neighborhood. We look what is the ensemble of states there, and we use the local update rule to determine what is the next state of that cell at position V. And we write we will usually denote the CA like this. So this is a typical notation of a dynamical system. This is the set we operate on, and this is the map on that set. Not every dynamical system of this form is a cellular automaton. You have to have the underlying local rule F that defines the global update rule in this way. So typically we will look at one-dimensional and two-dimensional cellular automata. So in one dimensions, the cell or the grid is essentially just Z. In two dimensions, it is Z squared. For practical purposes, when we visualize the dynamics of this system on a computer, we cannot simulate the infinite grid, right? So we typically assume cyclic boundary conditions. So we essentially just operate on a grid Zn. So we just take all the indices here modulo some n. And cyclicity essentially means, well, this cell somehow, let's say the neighborhood is just -1, 0, 1. So each cell just sees its own state, the state of its left neighbor and the state of its right neighbor. So this cell would not have its left neighbor, so we kind of assume that the left neighbor of this cell is this cell, so essentially we view the grid like this, and in two dimensions it's the same thing. We typically just simulate a finite grid, some Zm times Zn, and again we kind of assume that we connect this side with this side and this side with this side. So essentially this means we are operating on this discrete torus, which I will not really attempt to draw, but So for Neumann's cellular automaton, the one he defined and in which he described the self-replicator is a two-dimensional CA with the now so-called von Neumann neighborhood. Which essentially just means that each cell sees its left, right, top and bottom neighbor. So technically this is This is the von Neumann neighborhood. So you will have plenty of time to get used to cellular automata through a plethora of examples. But for now, let us focus on the design of von Neumann CA. So, okay, so let's just maybe show one example. So, usually when we depict cellular automata, the appeal comes from the fascinating visualizations. So here you see a one-dimensional cellular automaton with states 0 and 1. Those are depicted by white and black. The initial configuration is a finite cyclic configuration of size 250, and it represents the first row of this diagram. And then essentially time flows downwards, so each subsequent row is just the image of the previous one under the global rule. So here the local rule is with the exact neighborhood I showed there, just the left and right neighbor and a cell itself, and the update rule is just to take the sum of the left and right neighbor modulo 2. For 2 dimensions, we typically depict the space-time diagrams as just videos, where each snapshot is a time step. So let us define von Neumann's cellular automaton. It has von Neumann's neighborhood and 29 states. So we will define them progressively. If we had to specify the rule table explicitly, it would take a few years or thousands of years. So we will take advantage of some symmetries and just provide, let's say, a high-level definition of the local rule. Okay, so the first state is this gray background that you see everywhere. This is the so-called quiescent state, and it has an important property, is that if you put this state into the local update rule, the image is again this state, which means this acts as a static background. So I'm now showing you the software Golly. When I click on step, it does one iteration of the CA, and this background just stays gray. So this is, let's say, the most basic state is this gray background. And the first family of states are the so-called transmission states. Their main function will be to transmitting signals. So here we have 4 ordinary transmission states. In the lecture notes, these are represented by single arrows. In Golly, these are represented by the blue color, and they can point in 4 different directions. So by themselves, they are just stable. But now we can use them to construct the so-called ordinary channels. So that's just a line of such states. So by itself, this is not very interesting because they just stand still. But essentially, each such ordinary state can be either unexcited, this is the one you see now, or excited. So draw an excited state is essentially, here just depicted by a green one. And what happens if we have such an ordinary channel? This should be fine. And we look at the dynamics, it's just that the excited signal travels through the channel in the direction that is specified by that state. Great. So this is the main function of the ordinary states. They just transmit signals. In this way, we can represent signals as binary sequences where the presence of an excited state is a 1 and the absence of an excited state is a 0. So we can, for instance, say that this channel is transmitting the sequence 1, 0, 1, 0. I hope this is clear. So the second function of the ordinary transmission states is that it acts like a disjunction or like an OR gate. So here you see, okay, one more thing to explain is the notion of input and output signals. So typically for ordinary transmission states, input signals are from all the arrows that are pointing towards it. So here, essentially, this particular cell has two input channels, the top and bottom one. And what happens if we activate both of them at the same time? It just activates the signal. Done. Let's ignore what happened there. But if we just activate one of them, the signal still passes through. So indeed, as long as there is at least one excited input ordinary transmission state, the ordinary transmission state gets excited in the next time step. So this is how these function on their own. And in some sense, dual to them are the special transmission states, in the nodes depicted by double arrows, here by the red state. And by themselves, they function completely analogously. So again, they are stable, they transmit signals. Now the excited signal is represented by a purple color. And again, this acts like an OR gate in the sense that, yeah, as long as there is at least one excited special transmission state pointed towards one, it's going to get excited in the next time step. So hopefully this is clear. And now the interesting part comes from the interaction of the two. So essentially, in the cellular automaton, we will have to be able to implement movement. Somehow analogously to the kinematic model, we will actually be building a machine with a similar organization. There will be some functional part, there will be the tape, and there will be a construction arm that can move around the space and just create new states and essentially create a whole new pattern in the CA grid. So this construction arm has to be able to move. But movement in the cellular environment is quite strange because you essentially have to keep creating something in one direction and destroying it in the other direction. So for instance, we have to be able to implement destruction of an arbitrary state. And this is what is the interplay between the ordinary and special transmission states. So here we see an example of 4 ordinary channels that point towards a special state. And if we run this, the active excited signal just destroys each of them. And the same is true vice versa. I am missing one. So you can play around with this. I hope Esan showed you Golly in the first lecture. Yeah, so the excited states destroy each other. Good. Let's introduce another state, the so-called confluent state. Again, okay, or not again. I'm saying confluent state, but there's actually multiple of them. There's 4. This is how they look like. This is the standard version. Oh, why not? And this is its 3 other variants. Yeah, it's a bit painful sometimes. So, if we just run an ordinary channel with a single confluent state attached to it, it stays stable. But the first function of the confluent state is apparent when there is an excited signal traveling. So usually it should take, without it, it would just take 1 time step to travel through, but it acts as a delay. So it's going to take 1 more time step to pass through the confluent state. And this is why there is essentially 4 of the confluent states. Because of this delay, the confluent state has to remember 2 bits of information. What is the signal state 2 time steps back and 1 time step back that traveled to it, such that it can input them with the corresponding delay. So for instance, if we have 2 consecutive active signals, it will just transmit them by remembering that they were there intact. Hopefully that's clear. The second function of the confluent state is a conjunction. So essentially the confluence state acts as an AND gate. So again, we can consider all input channels into the confluence states to be such ordinary transmission states that point towards it, and we can consider output channels to be all ordinary transmission states that do not point towards it. So in this case, we have 2 input channels and 1 output channel. And if we activate just one of them, draw. Nothing happens. But if we activate both, oh no, both of them synchronously, such that the signals arrive at the same time, it will eventually be transmitted. So that's just an AND gate. And the last function of the confluence state is broadcasting. So we have to be able to multiply signals. So one incoming signal should be able to become 2 outgoing signals through 2 different channels, and this is exactly the role of the confluence state. So here we have 1 input channel and 3 output channels. This one, and this one, and they will all get activated if we send an excited input signal. Great, so now we know how ordinary states and confluence states interact, but we also have to specify how special states, yes?
So can you repeat why the previous example did not work with just 1 input?
That's the definition of the confluence state. It literally acts as the conjunction of all input channels. So this is how we're the gods of this world, or we're not, von Neumann was, but the way he defined the confluence state is that every incoming arrow acts as an input channel, and the confluence state will only output an active signal if and only if it received excited signals from all its incoming channels at the same time. This is a great time to just keep asking me questions as soon as you don't understand, because otherwise it will get piled up, because all of this will be used in later constructions of more complicated building blocks. So please ask me. Good. So let's move on to the interaction between special states and confluence states. So the confluence state, as every other state in the system, has to be destroyed by something, and this is where the role between ordinary and special states stops being symmetric, because if we activate a special channel that points towards the confluence state will get destroyed. However, the confluence state has essentially one more function, and that is it acts as a somehow communication switch between ordinary and special transmission states. So here you see an example where this confluence state has a single incoming channel of ordinary states and 3 outgoing channels, 2 of them special and 1 of them ordinary. If this channel gets activated, the confluence state will broadcast to all of them, regardless whether they are ordinary or special. So this is how information can travel from ordinary states to special states. So if we activate this, all 3 of them got activated. Yes?
Can the input also come from a red arrow?
If the input came from a red arrow, the confluence state would get destroyed.
What happens if it receives 2 inputs for a blue and a red arrow at the same time? And at 1 time step?
Great. So, okay, now you're noticing that I'm not telling you all the possible interactions. In some cases, what will happen is that the pattern we will construct will not utilize all possible, like there will not, it's not going to happen that you will ever see every single combination of states interacting with each other. So what we are doing is we're actually specifying a subpart of the rule table, and you can fill the rest however you want. So we're actually building a lot of von Neumann cellular automata, each of them having the property of being able to self-replicate. But actually your question is relevant, like this particular interaction is going to happen, I think, at some point, or we will discuss it at some point. So I think it is always the case that destruction or creation, as we will discuss later what creation means, has precedence over signal transmission. But let's see, it's nice that we actually have this interactive environment, so you can verify that I'm telling you the truth. Oop, this is not what well, this could also work actually, but let's, okay. So, we activate both. I was not lying, good. So, we have to be able to create something out of nothing, and the nothing here is the quiescent state. This will be realized by sequences of active ordinary signals and the so-called sensitized states. So the sensitized states, there is 8 of them. It is not crucial to remember how they really interact. What is crucial is to just understand what is their overall function. So I will just first show you on an example and then we can discuss it further. So you have already seen this before. If we have an ordinary transmission state with a single active signal, what happens is the quiescent state that it is pointing towards turns into the first sensitized state. So this sensitized state essentially represents the following situation. It is saying, I used to be a quiescent state and now I received an active signal. So my intention is to transform into some ordinary or special or confluent states based on the following bits of information that will arrive to me from the ordinary channel. And so essentially each active signal essentially triggers the quiescent state into this, and the following sequence specifies which particular state it should transform itself into. And in particular, the sequence of 4 zeros, so essentially just inactivity, will guide the sensitized state to change its state a few times. Essentially, this state encodes, I have received the first 0. The next state encodes, I have received the second 0. I have received the third 0. And now, as it's going to receive the fourth 0, it's going to transform itself into an ordinary transmission state pointing rightwards. So now you probably understand why all the previous examples had ordinary transmission states pointing rightwards, because then if I just show you active signals passing through, it's going to result in the channel just prolonging, whereas being messed up by other states. So the rule table is present in the lecture notes. I don't think you necessarily have to memorize it, but just for completeness. It is really good to persuade ourselves that there is no crucial detail we have omitted in the construction that it would really work, so it's good to specify this. So this S is essentially the initial sensitized state, and now you can follow paths. For instance, if the following bit sequence is 0, 1, 0, it's going to result in this state. If it's 1, 1, 1, it's going to result in a confluent state that is inactive, and so on. Is this clear? And we can just see all of these in action. So if we just have 0, 0, 0, 1, it's going to result in an ordinary transmission state pointing upwards, and so on and so forth. There's a mistake. Good. Let's correct it. Oh, I should not use this, but this. So let's look into our table. The confluence state should be encoded by the first one, which activates the sensitized state, and then 3 more ones. So we should have 4 ones. This sometimes happens with Golly, that it crashes, and there's nothing we can do about that. Wonderful. So now it's now I see my mistake. I just added 1 less activated signals. Perfect. So these are the 9 states we can create, and all the other states we can create from them by more active signals. So this is it. We have basically specified all the rule table that we will need. And this is the part where we really become engineers. We will start constructing more and more building blocks from these basic interactions. You will have a chance to really lean into your engineering side in the exercises, where, for instance, you can persuade yourself that you can build an arbitrary Boolean function or like a logical circuit just from the components that we have seen. Yes?
What happens at the end of a red string of arrows?
Ah, good. Perfect. Good question. So when it comes to creation, the role of ordinary and special transmission states becomes symmetric again. So it's gonna also create new states. So this will be the case for all of them. So the first simple building block that we will create is a so-called pulsar. This is a unit that can transform a single active signal into an arbitrary sequence of signals that you specify. So formally, it's defined in the lecture notes. So let C be a binary sequence, which is non-empty. The pulsar PC is a pattern with the following behavior. When it receives a single input signal pulse at time t, it produces the signal sequence C as output at some t plus delta t for some fixed delta. So in this particular case, this pulsar corresponds to the sequence 1, 1, 0, 1. And as you can see, this incoming signal will exactly get transformed into it. It's pretty easy to explain why. There are 3 ways this active signal can travel to this output channel, and each of them has a different time delay. So the fastest way is to go through here, which is exactly this first signal that arrived here. Then the second fastest path is through here, where the signal has to travel through 1 extra confluence state, which will add 1 extra time delay. So this is responsible for the next active state. Then we omitted the third one because we are encoding the sequence 1101, so we do not want to have an active signal here. And then lastly, the slowest path will result in this signal. Hopefully that's clear, and hopefully you are now able to construct a pulsar for an arbitrary sequence on your own. A somewhat almost dual component to it is a decoder. So the decoder's function is that if it receives a particular sequence, if it has a specific form, it's going to emit a signal, and if it doesn't, it's not going to emit a signal. The role of the pulsar and decoder, or a recognizer, which is an upgraded version of a decoder we will also talk about, is that we can encode information such that it can okay, so this is how it's going to look like. We will have multiple components that have to communicate with each other and some channels that connect them. And there will be signals traveling through the channels. Now, if the information was not encoded, if a particular component receives information, it will not know, is this information supposed to be for me or for some other component? So this is why if we encode the information such that only this particular component having a particular decoder receives it, it's only going to decode it for its own usage, and all the other components having different decoders will ignore that information. So the decoder is defined as follows. So first we say if we have two binary sequences of the same length, then one is smaller or equal to the other one. If whenever C has a 1 at a particular location, C prime also has a 1 in this location. So C prime has to have 1s everywhere where C has it. And the decoder will act as follows. For some fixed sequence of length n, which is non-zero by the way, the decoder DC is a pattern with the following behavior. If it receives an input sequence C prime of length n, it produces a single pulse at some time t plus delta t for a fixed delta t, if and only if this input sequence was greater or equal to C. So, as you have noticed, we have not yet found a way to kill signals, so it is not possible to transform a sequence of active signals into inactive signals. This is why this decoder only cannot recognize one precise sequence, but can recognize all sequences that are more active than the sequence it encodes. So here we have a decoder that is connected to the sequence 1101. And indeed, if we put on the tape the sequence 1101, the information will meet each other in such a way. Oof, okay. I had a long night yesterday creating these, so I'm glad they work so far. Yeah, so this, but if we, for instance, put a larger sequence, let's say 4 ones, it will also result in an active signal. However, if we put any sequence that is strictly less than 1101, for instance 1010, this decoder will not get activated. And you can probably see how it works. Again, there is 3 paths that a signal can follow, but now instead of disjunction, this is implementing a conjunction of signals. So in order for, let's say, a signal to pass through this confluence state, it has to have 2 active signals arriving to it at the same time, one arriving from this path, one arriving from this path. Essentially, this path has 1 extra confluence state, so this will have 1 extra delay as opposed to this path. So exactly if we have 2 signals of consecuting activation, the first faster signal will take the slower path, and the second signal arriving later will take the faster path, and this will result in them arriving at the same time to this confluence state. Right? And they are still also traveling through the other paths. So indeed, this confluence state gets activated. But now there is no 4th signal that will ensure that there is another signal arriving here at the same time as here, so the signal dies out. And that will only work if this 4th signal is active. This is the signal that will arrive here at the same time as the conjunction of these 2, and this will result in the active signal. I hope it's clear. Good. So this is a yet more complicated component, which will help us to build both the NOT gate, which is still a gate we somehow don't have, and store memory. So we would like to have some kind of pattern, which when it gets activated, it will kind of stay activated and store 1 bit of information, which is 1. But then you can also kind of turn it off, and then it's going to store the bit 0. And we should be able to probe this information by some external inputs. And this is exactly what this periodic pulsar will do. And it is already kind of, this is usually what human engineering does. You create some components, and then you compose those components to have more complicated components. This is exactly what is happening here. You can actually notice that this upper part is nothing else than a pulsar. It's just a more compact version of one. So what this pulsar does, do you know what it does?
Creates one.
Perfect. It transforms one input signal into 5 active output signals. And these 5 output signals, by the way, will exactly construct or create a confluent state. Just this is important to know. The second building block is this little whirl, which is essentially something like a clock. Oh, okay. Almost. Good. So, what's going to happen is that if we have an active signal, this signal will get propagated out, but will also circle back in, and will again propagate out and circle back in. So, essentially, we can interpret this as a clock that outputs an active signal every 4 or 5 time steps. Let's see. So 1. So in this particular sense, it results every, let's say, 5 time steps. What we can also do is we can load it with more input signals. And then it's just gonna keep being completely active and just keep on generating active signals. So this is essentially, okay, we are missing a few. Now it's fully active. So this is essentially what will store the 1 bit of information that will be stored in this activated loop that keeps on being active. And these are all the components. Oh, okay. Let's clean up the... Great. So what's happening here is that we have 1 pulsar, a second pulsar, which is just flipped below it. We have this clock. And what's going to happen if we activate it? So the, let's say, activation channel is this lower one, is that it's going to multiply this signal enough times to fully activate this clock. Now you can interpret this as the readout part, where if you want to know if this periodic pulsar stores a 1, you can just probe it with 1 active signal traveling through the top. And clearly, it will create an active signal in the output channel if and only if this whole thing was active. Oh no. Okay. Right. Now, how can we turn off this thing? So this is where this special use of the special transmission state comes in place. Essentially, in order to destroy a signal, we have to destroy an element through which the signal passes and then rebuild it. So, as we will see, this periodic pulsar again transforms into 5 active signals. First of which is going to activate the special state, and the special state is going to destroy this confluent state. Now what's going on is there are 4 more active signals coming both through the top and actually 3 more active signals coming through the bottom. So when such a situation happens through creation, the creation is kind of, a sensitized state is taking the incoming signals in a disjunctive form. So as long as it's receiving an active signal from somewhere, it's interpreting it as a 1. So what is really going to happen here is that this sensitized state will receive 4 consecutive 1s, and that will result in the creation of a new confluent state. But in the meantime, this whole activity died out, so we have kind of turned it off, and now this periodic pulsar is storing a 0. So now if we probe this, it's going to output a 0. And again, let me just use 5 more minutes of time, and then maybe the exercises can start a bit later, just so that we're done with this Golly demonstration today. There's just one last unit that I would like to show you. This is a recognizer. This is the most complicated one. So a recognizer is the true dual of the pulsar. What the recognizer really does is that if we pick a particular sequence C and we build the recognizer RC, it will produce an active output pulse if and only if the input sequence exactly matches C. So if there is more activity in the input signal, we have to somehow be able to detect it and kill the signal. And we will use the periodic pulsar, or let's say the principles from the periodic pulsar for that. So what is happening here? This part here is actually a decoder. Okay, so this recognizer that I'm showing you is a recognizer for the sequence 110000. So this particular part is a decoder, which is a decoder of the sequence 1100. So the easiest part that happens is if we have not enough active signals, it will not pass through the decoder, right? The decoder just kills it. And there is no way that the information can pass through. So we are good. Yeah. But if we have, for instance, 1, what happens is that this decoder will rightfully decode it and activate this confluence state. Now, this confluence state will trigger this active path here, which is the path that is attempting to output an active signal. But at the same time, it's going to trigger the upper path, and the upper path will always attempt to kill that signal if there were extra activations. So how that killing works is that there is a pulsar here, which is also a 1100. You can think of Y. But this is arranged in such a way that if there were more active signals, it will trigger the activity to arrive at this location at the exact time step that the active signal arrived from this location, trigger this destruction branch, which again transforms an active signal into 5 pulses, and these 5 pulses will activate the special transmission state. This will destroy the confluence state at the right time step and then rebuild it such that no signal passes through. So what happens when we input the right sequence? So there is an active signal through the decoder, and there are some attempts at killing the branch through here, but because they come from the correct positions, they will actually arrive here too early, and these two signals will not meet. So indeed, this branch has already died out when this branch arrived here. So there is just a single happy signal traveling towards the output. In contrast, if we input, let's say, 4 active signals, this, or let's say just 3 active signals, this third signal will use the slower branch of this to actually arrive here at the exact time step that it has to activate the destruction branch. So the destruction branch is activated, the signal is killed, and we are done. You can think about the details of this. This construction is also showed in the lecture notes. You can build your own recognizers in Golly, whatever you enjoy. So how can we use this to represent the NOT gate? So this is one last piece of information. It will not be useful to represent actually the information which contains the bit 0 as just an inactive signal for the following reason. If there is a component, it has no way to distinguishing whether the input signal, whether there is no input signal or whether the input signal is an inactive 0. So it will be useful just in general to encode the bit 0 by 2 bits. The first bit being active. And essentially, this bit signifies, behold, the signal after me is actually encoding the information 0 or 1. So you can really consider this as the presence of a bit of information as opposed to complete inactivity. And this way we can also encode the bit 1 as just 2 ones. And now it's pretty clear that just using some smart recognizers, we can transform the sequence 0, 1 into 1, 1 and the sequence 1, 1 into 0, 1. I will let you think about this. But at this point, we should have persuaded ourselves that we can transmit signals, build all the logic gates for and, or, and not. We can store 1 bit of information. And next time, we will use this to construct even larger functioning units that will eventually result in a construction of this. That will be too big for us to see. But we will just have to rely on the fact that if we can describe its parts, we believe in its existence. So that's it for today. Thanks for bearing with the extra 6 minutes.